In this lecture, we're going to get the payoff from the previous two on inflation and string theory. When we talked about string theory, we realized that the thing that we would like to be the case, namely that what we think is the unique string theory that lives in higher numbers of dimensions, predicts things like what is the dark energy and what is the dark matter, doesn't quite turn out to be true. String theory predicts too many things. As far as we can tell, it is compatible with all sorts of different possibilities. But nevertheless, it has an impact on how we think about dark matter and especially about dark energy. What we'll talk about in this lecture is how ideas from string theory and inflation change our notion of what constitutes a natural value for the vacuum energy. Remember, after we talked about dark energy existing and going through all of the different possibilities for what it might be, the possibilities of quintessence and changing gravity were interesting but ran into problems with experiments. The possibility that it is vacuum energy, an absolutely constant amount of energy in every cubic centimeter of space, didn't run into any problems with experiments, but seemed very, very unnatural. The value the vacuum energy would have to have is just very, very different from the value that it seems to actually do have in our universe. So string theory has the chance to recalibrate our notion of what it means for a number to be natural. And this is a long process that we're going to go through in this lecture. So the punchline is that string theory says there can be many different phases. All of the different ways of taking the extra dimensions of string theory and all the different branes and other things it predicts and compactifying them down to get a four-dimensional space-time like the one in we live can correspond at low energies to different phases of space-time. Just as water can come in different phases of liquid water, solid water, of ice, and water vapor, it's the same underlying thing. It's not like there are three different theories, a theory of water vapor, a theory of ice, a theory of liquid water. It's the same stuff manifesting itself in different forms. Likewise, what string theory is saying is that there are perhaps 10 to the 500 different phases of space-time. All these different ways in which the fundamental vibrational modes of the string can show up as particles, as numbers of particles, and as the vacuum energy. The vacuum energy is going to be a number that changes from phase to phase, from compactification to compactification, so we'll take on all sorts of different values, 10 to the 500 different possible values. Within that ensemble, we're going to get a lot of different possibilities. One of them might be the one in which we live. This idea is sometimes called the anthropic principle, the idea that we're picking out, among a huge ensemble of possibilities, those possibilities which allow us to exist. The reason why that's a sticky situation is because we don't know what us means in that sentence. What do you mean us? What kind of conscious observers, what kind of definition do you have for what counts as intelligent life? So we're not going to go into any of those issues in any detail, but we're going to rather think about it in terms of environmental selection. It's not a surprise that if you live in a universe or in a set of universes in which conditions can be very different, that we're going to observe those conditions that are hospitable to us living there. That is just a tautology. That is not surprising. The interesting part is when we go from the tautology to using it to make predictions. Within this ensemble, what is likely for us to observe? We might be able to change our notion of what you would expect ahead of time by realizing we live in an ensemble of many possible universes rather than in one unique thing. So we live in a universe that we can't see the whole thing. We live in a universe where the observable part is defined by a horizon. We send back light rays into the past, and because the speed of light is finite, those light rays hit the Big Bang, hit a boundary at a finite distance. There is almost certainly parts of our universe which we can't see because they're simply too far away. That is not a surprising claim or controversial in any way. We can certainly see out to the cosmic microwave background. If we're trying to be clever about it and we learn how to use neutrinos or something like that, we can push that back a little bit further, but there's still a very clear demarcation past which we can't possibly see, which is given to us by the Big Bang itself. So what is beyond that part that we can see? The part we can see seems to be homogeneous and isotropic. Not only is the configuration of stuff more or less the same density of stuff from place to place, but it seems from our observations as if the laws of physics are the same. It's not true that the charge of the electron is a different value in one part of the universe than in the other one. As far as we can tell, they're the same everywhere. So is it possible that you can just extend that understanding infinitely far? Is it conceivable that we live in a universe where conditions really are the same everywhere, even outside what we see? The answer is absolutely yes. There's no reason we can give, either logically or within the laws of physics as we currently understand them, against the idea that the universe is truly the same everywhere, even outside what we observe. But by exactly the same criteria, there's no possible reason we can currently give to say that the universe is the same everywhere. It is absolutely just as reasonable to say the universe is very, very different outside. On the one hand, you might say that it is very parochial, very anthropocentric of us to take our local universe and to extend it all over the place. On the other hand, you might say that it's not very parsimonious to have a universe which is wildly different. We have a universe which looks very nice as it is. Why not just take the simplest possibility and extend it all over the place? The point is that we can't answer this question just by pure thought. So when we're in a situation like that, what we have to do is to allow for both possibilities. We don't need to make a decision. We're going to ask what happens if the different things are possibly true. So for this lecture, we're going to ask what happens if there are different regions of the universe where conditions are very different. So we're going to call this the multiverse, but it's not a multiverse in any metaphysical sense. It's not like there are different universes that are separate from each other by some profound difference. They're just different regions of space into which we cannot get. That's an interesting thing to think about as a possibility, but it's string theory and inflation that takes this possibility and makes it very tangible. In other words, string theory plus inflation gives us a set of ideas from which we can talk about the possibility of a multiverse in a scientific way. It is string theory that allows space to take on different conditions, not just different densities, but different phases. So the different ways we have of taking the extra dimensions of space in string theory and curling them up give us different low-energy physics. In our current world, we seem to have 4 dimensions of space-time, so 3 of those dimensions are large dimensions of space, and we have the standard model of particle physics. The standard model is characterized by a set of particles and also by a set of numbers. So we say we have certain fermions, we have certain bosons, etc., certain interactions relating to particles, and also certain parameters. Those parameters are the charge of the electron, the mass of the electron, the mass of the up quark, and so forth. One of those parameters is the vacuum energy. So when string theorists realized that there was more than one way to compactify the extra dimensions, they realized that in fact, if there was going to be more than one way, there's going to be a huge number of ways. Something like 10 to the 500 is the current best guess. So to this set of possibilities, they've given the name the landscape. The string theory landscape is something you can think of as like some jagged landscape here on Earth, and every little minimum, every little local valley is a different place you can live. Different valleys, of course, are going to have different local conditions, different temperatures, different densities, different heights. So that's an analogy to what we have in string theory, where there are different ways to curl up the extra dimensions, perhaps not an infinite number of ways, perhaps it's not anything goes, but the number of ways we can get is still very large. 10 to the 500, 1 followed by 500 zeros, is a huge number of possibilities. Now I should say that we're very far from being certain that this is true. Currently, our best understanding of string theory says that there are perhaps 10 to the 500 different ways to curl up the extra dimensions. However, it is certainly conceivable that the current state of the art just isn't good enough to say that for sure. In other words, it's possible that once we understand string theory better, we will come to understand that even though you can curl up things in different ways, they don't stay curled up like that. You might curl up the extra dimensions in a certain configuration, but they quickly unwind into a different one. It is therefore still quite possible that once we understand string theory better than we do today, we will narrow it down to a very small, perhaps even unique set of possibilities. That is a goal to keep in mind if it's true, but the current best guess on the basis of what we seem to understand right now is that these different phases of string theory really are stable and really can exist in principle. So what inflation does is take phases of string theory that can exist in principle and gives them a way to actually exist in practice. What inflation says is that at very early times in the history of the universe, we don't know exactly what was happening, but perhaps there were chaotic fluctuations. Different conditions were going on all over the place. It was very high temperature, very large fluctuations from place to place. In some tiny little patch of that initially chaotic system, you got a domination by something like dark energy, some inflaton field with an approximately constant energy density. And that inflaton caused that little patch to accelerate, to expand to a huge size. Eventually, the energy in the inflaton reheated into matter and radiation, and we see what we see today. So if you take the idea of inflation and combine it with the theory of 10 to the 500 different possible stable final states for the compactified dimensions of string theory, what you get is a way to make those possibilities real. By starting inflation in slightly different conditions, by allowing inflation to go on in slightly different ways, you can have different trajectories, all of which populate any one of the 10 to the 500 different valleys in the landscape. In other words, we're imagining a multiverse that starts out in some chaotic condition, and then through inflation happening in different parts, in different ways, using different physics, we get a final condition in which you get huge bubbles of universe, all of which could be in any one of the 10 to the 500 different phases of string theory. Clearly, there are a lot of details to be filled in when we talk about something like that. Right now, there's a lot of hand-waving involved. We don't know the correct picture, but that kind of picture is perfectly plausible. It might very well be, according to what we understand right now, that the universe we observe is a tiny infinitesimal fraction of everything there is. It is arguable that that is the lesson of Copernicus. If you're not putting us at the center of the universe, you shouldn't assume that the conditions that we observe are the same conditions that obtain all over the universe. So one thing I want to talk about is whether or not this is legitimate, whether or not it's okay to talk about regions of the universe which we cannot see. People will say, if you can't observe these different regions of the universe, they have no effect on local physics, they have no effect on what is going on in your region of the universe, and they never will. Therefore, talking about them isn't even science. So who cares about whether or not they're there? Well, the reason why we would possibly care, and we'll talk about this in more detail later, the reason why we would possibly care is because living in an ensemble changes our notion of what is natural. If you only live in a unique universe, then you might guess that the constants of nature will naturally take on the values that would seem easy to us if everything was of order 1, if there were no large differences between the different numbers that you saw. But if you live in an ensemble, then every possibility happens, even some extremely, extremely rare ones. And if one of the extremely rare possibilities is somehow more hospitable for us to living there, then we should not be surprised if we live in one of the rare possibilities. It would be very natural for us to live in a universe in which the parameters of nature somehow didn't seem natural. That's why it's worth thinking about this possibility that we live in an ensemble, a multiverse of different phases of string theory. Other people will say in a related way that it's not a scientific theory if it doesn't make very particular predictions. But I want to point out that the multiverse is not, strictly speaking, a theory. The multiverse, if it's there, is a prediction of a theory. The theory is string theory combined with inflation. Now, that's not a very exact theory right now. We don't understand either inflation nor string theory well enough to tell you precisely what the predictions are. But the goal of this kind of way of thinking is the following. Someday, we will be able to do experiments that convince us that a certain theory of quantum gravity is correct. Hopefully, we will be able to narrow down, on the basis of data, on the basis of experiments, which version of string theory, if any, or which version of quantum gravity correctly describes our world. We will, within those experimental constraints, be able to say the following fields can act like inflatons, can make the universe expand. In other words, on the basis of data, we will build a framework which makes a specific prediction for what the multiverse should be like. Within that prediction, we can begin to make sense of questions like, what should people observe who live in that ensemble? So even though the prediction of the multiverse is itself not testable, it might be an airtight prediction of a model that has other testable predictions. That may or may not be a utopian goal, but that is the kind of thing that we're shooting for when we think about these ideas in the back of our head. Okay, so now the philosophy is a little bit out of the way. Let's try to talk about putting this to work. What if we really do live in a multiverse? What if there really is an ensemble of different places that we don't observe where conditions are very, very different? Well, it goes without saying that within that ensemble of different possibilities, there will be very strong selection effects when you ask what is observed by a typical member of that ensemble. We imagine, roughly speaking, that some of these places in the multiverse are very inhospitable. We just can't live there. So it is not surprising that no one is observing them, if observers cannot exist. Now we admit that there is a very, very big question here of what is an observer? What is somehow what people call a conscious person or some intelligent scientist who can live if the laws of physics are very, very different? You could ask very detailed questions about this. For example, imagine a universe that was almost exactly like our own, but in which the proton was a little bit heavier than the neutron. This is something we talked about when we were talking about the standard model of particle physics lectures ago. What would happen is a proton would then decay into a neutron. Heavy particles decay into light ones. So instead of a world made of atoms, where you had atomic nuclei surrounded by electrons, you have a world made of neutrons. It should be clear that a world made of neutrons is very different than the world in which we live. You can't have chemistry in a world made of neutrons. You might therefore ask, can you have intelligent observers in a world made of neutrons? So some people think they know the answer to that question. I do not think that I know the answer to the question, can you have intelligent observers made of nothing but neutrons? I could hypothetically conceive that neutrons could get together. You could have little nuclei made of 1 or 2 or 3 neutrons, that these nuclei could even get together to make neutron molecules, and those molecules could build up into neutron amino acids. I truly don't know whether or not there is a sufficient room for complexity in a universe made almost all of neutrons to support intelligent life. And therefore, I don't care. Therefore, I'm not going to talk about any predictions you can make at a very tightly quantitative level that say if we increase the mass of the proton by 10%, then life cannot exist. We're going to keep an open mind about that. We're going to stick to things which I think every reasonable person would agree on do say something about whether or not conscious observers can exist. In particular, we're going to talk about the vacuum energy. The vacuum energy is one thing which we think has a very, very unnatural value. The vacuum energy, if it is the dark energy, is 10 to the minus 120 times what we would have thought would be its natural value. That seems preposterously finely tuned from the point of view of ordinary particle physics. If everything were natural in the standard model, the vacuum energy would be at the Planck scale. It would be 10 to the 120 times bigger than it is today. However, nobody who I've ever met claims that life could exist if the vacuum energy were that big. If it were that big and a positive number, the acceleration of space would make it absolutely impossible to form planets, or for that matter, individual atoms. You couldn't even make a proton in a universe where the vacuum energy was the Planck scale. Everything would be ripped apart very, very quickly. You'd be left with an empty universe almost instantaneously. There's no room to form life in such a universe. If the vacuum energy had the magnitude of the Planck scale but were negative, it would make the universe recollapse in 1 Planck time, much too small of a time scale to have any realistic or interesting particle physics, much less actually form life. In other words, when it comes to the cosmological constant, we have a very strange situation. We have a natural value for it to have. The cosmological constant is just a different word for the vacuum energy, and it should be at the Planck scale. That's its natural value. But if it had its natural value, we would not be here to talk about it. So on the one hand, it's not surprising at all that the cosmological constant doesn't have its natural value. It can't have its natural value, or we wouldn't be here thinking about it. The question is, why do we live in a universe in which the vacuum energy, the cosmological constant, is small enough to allow us to be here? And there are basically 2 different possibilities. One possibility is we just got lucky. In other words, there is no reason why the vacuum energy is small enough to allow for the existence of life. It just happened to be that. Within that possibility, the just got lucky idea, there are two sub-possibilities. One says, we truly just got lucky. It's not only that the vacuum energy is small, but it's just a random number. There's no dynamical physical explanation for why it's small. It was just randomly chosen, and happily, it turned out to be 10 to the minus 120 what it should have been, therefore we can exist. That is an absolutely possible theory of the value of the cosmological constant. I can't tell you that that theory is wrong, but for obvious reasons, it's kind of unsatisfying. That would be a truly lucky roll of the dice for us, for the vacuum energy to be that small. The other possibility within the idea that we just got lucky is that there is a dynamical mechanism. The thing that we got lucky about is not that the cosmological constant is a random number that is small, but that the cosmological constant is small because there is some physics that we haven't yet figured out that makes it small. We're lucky for the existence of that physics, not for the random throw of the dice that make the vacuum energy very small. But right now, we don't know what that physics is. We're just guessing at it. Many people are hopeful that we'll find it at some point, but we just don't know. The other possibility besides that we just got lucky that the cosmological constant is small is that we had to get lucky in the sense that the cosmological constant is not a once-and-for-all constant of nature. It's an environmental variable that takes different values in different places. If the cosmological constant takes different values in different regions of the multiverse, and in some of those regions it's small enough that life can exist, then it's not a surprise. Then it's not that we got lucky that we exist in those regions. Let me give you an example. Imagine that, an analogy. Imagine that there were astronomers who lived on a planet where the atmosphere was opaque. You could never see the sky. And on this planet, the temperature was very mild and never changed. It was 70 degrees every day, but you couldn't see anything besides the clouds overhead. In such a universe, in such a hypothetical situation, what would the scientists who live on that planet try to do? They would try to understand the temperature that was on their planet. They would say, are there laws of physics that predict that the temperature will always be 70 degrees and we can be here? Well, other physicists on that planet would say, my idea is that there are also other planets. And on those other planets, the temperature is very different. But there are just so many planets that life is going to arise on the planets where the temperature is nice. Other people will say, oh, come on, that's just philosophy, that's not science, we can't see these planets, how should you be talking about that? Our current situation is actually much like that. Just like there are clouds in the sky of this hypothetical planet, we have a horizon given by the microwave background past which we can't see. Maybe there are other regions of the universe out there where conditions are very different. The fundamental question before us now is the vacuum energy a once-and-for-all constant of nature, for which there should be some equation that predicts its value, or is it an environmental variable? Is it different from place to place, and therefore chosen by a selection effect rather than a deep law of physics? So if we're going to decide between those possibilities, it would be nice to take this idea that there really is an ensemble of different possibilities, and actually use it to make some sort of predictions. To not just use it to make us feel good about the value of the vacuum energy, to actually do something precise with it. Well, what you want to do is to consider the entire ensemble, and within that ensemble ask, what does a typical observer living in that ensemble of multiverse actually observe? So this exercise was undertaken in the 1980s by Steven Weinberg, a well-known physicist who actually won the Nobel Prize for his work on the standard model of particle physics on the W and Z bosons. What Weinberg says is that we can actually attach numbers to this statement, that if the cosmological constant were large and positive, it would rip things apart. If it were large and negative, it would make the universe recollapse. He did a little calculation, and he argued that the typical value of the vacuum energy that would be observed by a conscious observer is something like 10 times as big as the matter density, by which he means the vacuum energy could be anywhere from minus 10 times the matter density to plus 10 times the matter density. So you pick a random number between minus 10 and 10. A typical random number between minus 10 and 10 is not going to be 10 to the minus 5. It's going to be of order 1. It's going to be minus 3 or plus 5 or something like that. So Weinberg in 1988 made a prediction that someday we would observe a non-zero cosmological constant. That was a prediction that he made before we went out and found it. Then 10 years later, we did find it, and in fact, it was consistent with his prediction. The vacuum energy we think we have observed is 2 or 3 times the matter density. That is consistent with being between minus 10 and 10. Not only is it between there, but it's kind of a typical number you'd expect it to be if you picked a random number between minus 10 and 10. So what does that mean? It means that you can predict something, at least you can try. You might want to predict other things. For example, you might try to predict the masses of the elementary particles, the mass of the electron, the mass of the quarks, and so forth. Even better, you would like to predict something we haven't yet observed to make sure we're still on the right track. The problem is the environmental selection that says we can only exist where conditions allow for us to exist isn't a very strong constraint on things we haven't yet observed. What is the dark matter? Is the dark matter a WIMP? Is it the lightest supersymmetric particle? Or is it an axion? The environmental selection principle doesn't tell us which one. We can exist just as well with both axionic dark matter or supersymmetric dark matter. You could even ask, how much dark matter should there be? Some brave souls have tried to argue that the environmental selection principle predicts there should be dark matter. The reason why is because the more dark matter you have, the more structure you form in the universe, the more galaxies, and therefore the more observers. To me, personally, this seems like a stretch. This seems more like a post-diction than a prediction. We already know there is dark matter there. You're trying to justify it after the fact. But I think that for vacuum energy, there is some possibility of something going on there. We don't know exactly what will go on. We don't yet know how to predict things we haven't observed, but it's still interesting to try to push our current knowledge of how the ensemble would work past what we get. Nevertheless, let me give equal time to the objections to this way of thinking. I should say that currently within the physics community, there's a sharp divide. There's a set of people who take very, very seriously the idea of the multiverse as an explanation for the observed vacuum energy. There's an equal number of people, maybe even a larger number of people, who think it's completely crazy. So I want to give you the arguments from the people who think that even talking about this is not what we should be doing. There's 2 basic kinds of objections to talk about the multiverse, what I will call the grumpy old man objections and what I will call the sensible objections. The grumpy old man objections are the ones that just say, doing stuff like this isn't science. You can never observe the stuff out there. You're giving up on our attempts to understand the universe based on evidence and observation and experiment. These are unconvincing to me as reasons to not think about the universe, but the multiverse. First, because it might be like that. It might be the case that outside what we can observe, the universe takes on very different conditions. Whether or not we can observe them, it might be the truth. And ultimately, our goal is to get at the truth by whatever method we can. If the way that we get there is by naturalness arguments rather than direct experiment, then that's what we have to live with. The second is that the multiverse is not, as I said before, a theory that makes strong predictions. It's a prediction of a theory that we can use to recalibrate our notions of naturalness. The point is that when we look at naturalness, when we look at quantities we measure in nature and say, that one doesn't look right, that looks unusual to us, we're taking that as a clue. We're saying that we really don't understand the final laws of physics, but we're trying. Sometimes the way that we are moving toward the final laws is to do an experiment that gives us more information. But other times, the way that we move towards a better understanding of the final laws of physics is to look at unnatural features of our current understanding. For example, that's what happened with the horizon and flatness problem in inflation. We thought that there was a good understanding of how the early universe behaved, but we didn't know why. Thinking about the reasons why the universe would be flat and nearly homogeneous led us to inflation. Thinking about the value of the vacuum energy might very well make more sense in the context of a multiverse that might lead to a better understanding of other things. The non-grumpy objections I take more seriously. There's a set of objections to thinking about the multiverse that I think are quite reasonable and we should take seriously. So basically what these objections are saying is that even if, in principle, we do live in a multiverse with various different things going on, as a matter of practice, it is impossible to extract from that any detailed predictions. And against this, you could say, well, Steven Weinberg, who won the Nobel Prize, made a detailed prediction. What about that? But there's a good objection to the fact that Weinberg made a prediction and sort of got lucky. The point is, he made a very specific calculation that did the following thing. He said, what if we had an ensemble of the multiverse in which conditions in all the different parts were exactly the same as they are here, except for the cosmological constant. He only allowed the vacuum energy to change, and he derived the prediction that the vacuum energy could be pretty close to the matter density. But that's not what the actual multiverse situation tells us to do. It says that from place to place, everything changes. Not just the vacuum energy, but the set of particles we have, the way that inflation works, and so forth. If you are allowed to change not only the value of the vacuum energy, but other quantities, like the value of the dark energy or the amplitude of the initial density perturbations, you would make a much less strong prediction. The true multiverse prediction for the value of cosmological constant is not nearly as precise as Weinberg's calculation makes it seem to be. So the truth is, we just don't understand the multiverse well enough right now to make detailed predictions using it. What we're doing is saying that there's this set of universes, set of places in the universe where conditions are different, but there could be an infinite number of such places. There could be an infinite number of observers in every one of those places. And we're trying to say, what does a typical observer in that ensemble actually observe? The state of the art is nowhere near right now being able to answer that question. It may be because we don't yet understand inflation and string theory very well, or maybe because we never will, that there isn't any right answer to this question. If there are 1 million observers who observe this, an infinite number of observers who observe this, and an even bigger infinite number who observe something else, how are we possibly to say which is more likely for us to be there? So this is all speculation at this point in time, but the reason why it's worth going over is because it's speculation that might turn out to be right. The real lesson is that we don't have any convincing theory of the vacuum energy, and we're driven to the environmental selection in the multiverse as the best we can think of right now. It might turn out to be right. The worst version of the anthropic principle would be to think that the universe arranges itself into the way that you think it should be. What we should do is to keep an open mind about all the possibilities as we get more and more data to help us zoom in on which one is ultimately correct.